What specific problem does the new method aim to solve?
The new method, source, segmented stationary unrolling for counterfactual estimation, aims to solve the problem of accurately attributing the influence of individual training data points on the behavior of a trained model, particularly in scenarios where traditional implicit differentiation-based methods struggle. Source addresses challenges such as models that have not fully converged or have been trained in multiple stages with different datasets. It combines the advantages of implicit differentiation and unrolled differentiation, providing a more comprehensive framework for training data attribution, TDA. Source allows for the attribution of data points at different stages of training, incorporates algorithmic choices into the analysis, and maintains a close connection with counterfactuals, even when assumptions made in implicit differentiation-based methods are not met. The method aims to provide a more efficient and effective way to estimate the impact of removing specific training data points on the model's behavior without the need for repeated model retraining, making it valuable for interpreting, debugging, and improving machine learning models.
How does the proposed method work? Illustrate step by step.
The proposed method, source, segmented stationary unrolling for counterfactual estimation, works by segmenting the training trajectory into multiple segments and approximating the reverse accumulation computations for each segment with statistical summaries. The method starts by organizing model checkpoints into distinct segments, representing different stages of training or changes in the Hessian and gradients throughout training. Within each segment, source estimates the stationary Hessian and gradient by averaging them across all checkpoints in the segment. The method then approximates the total derivative by considering the average effect of downweighting a data point within a given segment. This approximation involves computing the expected total derivative using statistical approximations for the Hessian and gradients within each segment. The method leverages the eigenvalue-corrected Kronecker factored approximate curvature (EK-FAC) parameterization to approximate the Hessian efficiently. By segmenting the training trajectory and approximating the Hessian and gradients as stationary within each segment, source can provide a comprehensive framework for training data attribution, TDA, without the need to store all intermediate optimization variables during training. The method offers advantages over implicit differentiation-based approaches, particularly in scenarios where models have not fully converged or have been trained in multiple stages with different datasets.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the source, segmented stationary unrolling for counterfactual estimation method lie in its ability to combine the advantages of implicit differentiation and unrolled differentiation for training data attribution, TDA. The method allows for the attribution of data points at different stages of training, providing a more comprehensive framework for TDA. Source can incorporate algorithmic choices into the analysis, such as learning rate schedules and the implicit bias of optimizers like SGD or ATOM. It maintains a close connection with counterfactuals, even in cases where assumptions made in implicit differentiation-based methods are not met, such as the optimality of final parameters. Additionally, source does not require storing all intermediate variables generated during training, leveraging only a few model checkpoints, making it more memory efficient for large-scale models. The method also addresses challenges faced by implicit differentiation-based techniques, such as analyzing non-converged models or models trained in multiple stages, providing more accurate and reliable attributions in these scenarios. Overall, source offers a robust and efficient approach to TDA, enhancing model interpretability, debugging, and improvement processes in machine learning applications.
How is the method validated or tested?
The method is validated or tested through various experiments and evaluations. The validation process includes comparing the proposed method, source, segmented stationary unrolling for counterfactual estimation, with existing training data attribution, TDA techniques using the linear data modeling score, LDS, and subset removal counterfactual evaluation. The experiments covered diverse machine learning tasks such as regression, image classification, text classification, and language modeling. The performance of source is compared against baseline methods like representation similarity, REPSIM, TRACIN, track, and influence functions, if, with the EK-FAC approximation. The evaluations are conducted under two settings: a single model setup and using checkpoints from multiple models. The effectiveness of source is demonstrated in scenarios where implicit differentiation-based approaches struggle, such as for non-converged models trained with a small number of update steps and models trained sequentially with different datasets. The validation process involves assessing the impact of removing training data points on model behavior and comparing the results with other TDA techniques. The results show that source consistently outperforms baseline methods in various tasks and scenarios, demonstrating its effectiveness and superiority in TDA applications.
What results were achieved with this new method?
The new method, source, segmented stationary unrolling for counterfactual estimation, achieved superior results compared to existing training data attribution TDA techniques in various scenarios. In terms of the linear data modeling score, LDS, source consistently outperformed baseline methods across different data sampling ratios. It demonstrated higher correlations with the ground truth, especially when using multiple segments for analysis. Additionally, source excelled in scenarios where implicit differentiation-based methods struggled, such as with non-converged models trained with a small number of update steps and models trained sequentially with different datasets. In these challenging settings, source outperformed other TDA techniques, showcasing its effectiveness in attributing model behavior accurately. Furthermore, in subset removal counterfactual evaluation, source identified top influential data points causing misclassification more effectively than other baseline methods, demonstrating its robustness and accuracy in identifying crucial training data points. Overall, source showed significant improvements in TDA accuracy and performance across various machine learning tasks and scenarios, making it a valuable and effective tool for interpreting model behavior and improving model performance.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the source method include the computational cost, especially when compared to influence functions with the same EK-FAC approximation. Source is computationally more expensive, as it requires computing the EK-FAC factors and training gradients for each model checkpoint when performing TDA on all segments. This can be a bottleneck for neural networks, as it requires storing a large number of optimization variables during training. Additionally, while source offers advantages in scenarios where implicit differentiation-based methods struggle, such as with non-converged models or models trained in multiple stages, it may still face challenges in scenarios where the assumptions of segmenting the training trajectory and approximating the Hessians and gradients as stationary within each segment are not accurate. Furthermore, the effectiveness of source may depend on the choice of hyperparameters, such as the number of segments and the approximation techniques used, which could impact its performance in different scenarios.